Good morning, grade 11s. Let's carry on having some fun and doing some science. So the first thing that we did is we looked at forces as a vector, where it was the drawings and the calculations that we did. And with the resultant forces, when we drew triangles, remember that the first method was tail to head. So if we look at the light blue arrow, we've got the tail of the one arrow and then to its head. Then the second one going down at a slight angle, its tail started at the head of the previous one and it went to its head. The resultant was then from the tail of the first to the head of the last. Let's not forget that. When we looked at the parallelogram method, we had the two of them, both coming from the same point, the two light blue arrows. They came from a single point and they went out. So now, remember in class, we even put someone down and two of us held his arms and we pulled him and he kind of went somewhere in the middle of the two. So we complete a parallelogram. Those light blue lines are parallel to each of its corresponding sides. And where those two lines cross, that is our resultant. Then the third way that we did it, and I know for a way that many of you preferred actually, is that we just put them all on a Cartesian plane and we took all the x components and we added them together. We took all the y components and we added them together and we calculated our resultant. Let's not forget, any resultant needs a magnitude and direction. Quite importantly on that is we then looked at equilibrium forces. Remember we said that F net here has got to be equal to 0 Newton. So it's a closed triangle because the tail of the first vector and the head of the last vector meet back together. Okay, you can also tell the difference between this one and the resultant ones of the previous slide because all the arrowheads are continuing on from one another. There's no one in the opposite direction. So F net is 0 newtons, and because we know it's the 0 newtons, we can use all sorts of things depending on the information given to do calculations. We also looked at components both on a flat slope and on a flat surface, and on a slope. On a flat surface, it was pretty simple because we just had f of x and f of y, where if the angle was between f and the horizontal axis, the x-axis, f of x would be f cos theta, f of y would be f sine theta. Going down the slope, we had to remember that the weight always goes straight down. Weight is never at an angle. It's straight down. So there's a perpendicular component, which was perpendicular to the slope. Perpendicular, remember, is the weight times cos theta. And we had a parallel component parallel to the slope, which is weight times sine theta. We looked at a whole bunch of different types of forces. The weight, I think we've discussed enough. It's just mg. And obviously on a slope, it has a parallel and a perpendicular component. We looked at the normal force, which is pretty important. When we talk about the normal force, we're talking about the force of the surface on the object. So we can remember that we did it in different ways. Number one, if the object was just chilling on the surface, it was just the same as the weight, just in the opposite direction. If it was on a slope, we had to look at it is exactly the opposite to the perpendicular component. So the perpendicular component of weight would be weight cos theta. The normal would be weight cos theta, but in the opposite direction. Where we had to concentrate a little bit here is when there was an applied force at an angle on the flat surface, because then we had to take the y component into account in calculating the normal, which could either lessen the normal if the y component was acting up, or it could increase the normal if the y component was acting down. Friction was pretty important because we had to look at static friction and kinetic friction. So if you remember correctly, static friction is when the object is stationary. In other words, I'm pushing on it like we pushed on my car, but I'm not pushing on it hard enough to make it move yet because that static frictional force is greater than my applied force. And then static friction max was that moment just before it started moving. It was the absolute max that the car, for want of a better word, could hold up against the applied force before it started moving. And then when it was moving, kinetic friction took over. Next thing after those, we looked at Newton's first, second, third law of motion. First law of motion was pretty simple. The terms we need to learn the law. We need to remember the use of the term inertia. And we need to remember that technically the equation for the first law of motion would be that F net is equal to 0. So if they say something is at rest or at a constant velocity, we know the resultant force acting on that object is 0 newtons. And we can then calculate the forces on it. Newton's second law of motion is probably the most important one that you had to learn, and it gets asked time and time and time again. So the equation F net is ma, and then remember we must always look at all the forces in one direction, subtracted from all the forces in the other direction. We had, what do you call those things? Simultaneous equations that we had to remember with this one. And again, there will be a Newton's second law simultaneous equation coming up in your matric final exams at the end of next year. Please don't let those slip. The last Newton law we did, Newton's third law of motion, again, learn the law. And then learn just basically it's the fact that if I push on you with 3 newtons, you pushing back on me with 3 newtons in the opposite direction. Newton's law of universal gravitation, F equals g m1 m2 over r squared, where we talk about all the masses, and every mass in the universe is affected by every other mass with an attractive force. So even online like this, I'm attracted to you because somewhere my mass and your mass exist and the distance is just huge, but it's there. There's a force of I miss you. I'm getting soppy now. Then another thing with Newton's law of universal gravitation, which is quite common in multiple choice type questions especially, is the proportionalities. So you need to remember that F is directly proportional to the product of the masses, and F is inversely proportional to the square of the distance between them. You need to go back and practice some of those. Then past papers. Past papers, past papers, past papers. What more can I say? They are super duper duper important, and they're very, very good practice as they give a good indication of what you can expect in an exam. So when you're doing examples and prep and things like that, always start with easier questions. So go through an exercise in the textbook and things like that. But don't rely on an exercise in a textbook to warm you up or to be enough to do well in an exam questions. Those exercises are just warm-ups. And they give you an indication of what's potting. They help you with the basic theory of what's potting. But in order to effectively prep for exams and things like that, you need to move on to some past papers. So for example, I've looked here at I think it's 2015's year-end paper question 2. It gives you the 3 forces. It asks you a question on it. And what is really nice is then you can check your answers. So as you are probably aware, on the WhatsApp group, I have sent you 2014, 15, 16, no, not 14. I think just 15, 16, and 17's year-end paper, physics and chemistry. But specifically for this, do some of the physics examples. Do the examples at the end of the section in your textbooks. Get yourself super duper duper au fait with this section. So have a lovely day. God bless. And enjoy physics with Farling, and enjoy physics. It's the best subject. Goodbye.